Section 6.9 is called temperature rise by resistance method. So the idea that we looked at or explored in section 6.8, where you're looking at a hot spot in an electrical machine, sometimes that is difficult to do, simply because to access that hottest spot and to incorporate some type of a temperature measuring device, thermocouple, whatever it is that you need to put in there, it can be difficult to do that within the existing design of the machine. Okay, so there's another method that can be used, and it's based on the average temperature increase in the windings. Okay, and it's all based on something actually that goes back to maybe your ELC 131 deal, to where an increase in temperature causes an increase in resistance. Okay, and if we can quantify that, we can develop this method, this resistance method, to look at the temperature rise in an electrical machine. So what we're looking at when we look at average temperature rise, we go back to that same curve that we had looked at before, or the same figure 6.7. And this time we're going to look at the second curve across here, and let's walk through this. And so what we're looking at here is this curve, right? 2 that travels up this direction here, and as you can see, instead of the hot spot, this is an average temperature rise of the windings, and it's a little, as you can see across here, across the different classes, it's a little bit less than the hot spot. But again, think about it being an average, and so that kind of makes sense as to what would be. He says, for instance, in Class B, the average winding temperature of 120 degrees is assumed to be equivalent to the hot spot temperature of 130 degrees. Okay, so for average temperature rise for a particular situation, this would be the difference between ambient and 120, and that amount would be 120 minus 40, or 80 degrees C for a Class B machine. Okay, so that's the way it works. It's just two sets of curves, different curves, that we have access to. So for Class B hotspot, we'd be looking at 90, and for Class B average, we're looking at 80. Now, this is all based on the average temperature of a winding is done based on this equation. And let me move this out to here. Okay, blow this up, get rid of this. And this temperature that's given to us as 6.5, it says T sub 2 is equal to R2 over R1, 234 plus T1 minus 234. Okay, I think I got all that in there. And what this is the T2 is the average temperature when the winding is hot, and T1 is the winding temperature when it's cold. 234 is a constant that's given to us that says that it's equal to 1 over this, which is equal to 1 over 0.00427, a number that we pulled out of that appendix earlier, that temperature coefficient. Okay, and I guess we're looking specifically at copper here, of course. Okay, so we do have to specify the material, right? So we're talking copper here. Okay, so copper is the value of this divided into 1, and that's where 234 comes from. Okay, R2 is the hot resistance, and R1 is the cold resistance of the winding. Okay, so we can make the determination of average temperature rise, using this resistance measurement method, and knowing that the hot temperature can be, immediately calculate the corresponding temperature by subtracting the ambient. If the temperature rise, for instance, class B was 80 degrees, then the product is acceptable. He says on page 130, he says, note that when performance tests are carried out using the resistance measurement, the ambient, again, must lie between 10 degrees and 40 degrees C if we're going to do this, okay? If the winding happens to be made of aluminum, equation can still be used, but this number becomes 228, and the reason he mentions, aluminum and copper are the two dominant types of conductors used. Okay, so we should work this problem that goes along with this, and let's explore that, and let me pause and let me rewrite some things and put it into position so that we can see it better. Okay, so let me set the conditions here. Okay, it says that a DC motor has been idle for several days, and it has an ambient temperature at 19 degrees. All right, and so we go to measure the shunt field resistance of this DC machine, and we discover that it is at 19 degrees C, 22 ohms of resistance. The motor then operates at full load, and when the temperatures have stabilized, the field resistance is measured again, and it is found to be at 30 ohms. And now we also recognize this is associated with a 24 degree C ambient. If the motor is built with Class B insulation, calculate the average temperature of the winding at full load, okay? So under full load conditions, this would be our initial equation, right? The 6.5. Then we put in 30, which is R2. We put in 22, which was R1. Then the initial temperature was 19. And so what we find, and this is copper, and that's why we have 234, we find that the average temperature of this shunt field at full load is 111 degrees C. Okay, now what we want to do, we're going to calculate what our temperature rise was based on what the ambient was for that. So this is 111 minus 24, which comes out to be 87 degrees C. Now, as I look at this, and I'm looking at Class B, right, the maximum allowable temperature rise, this is part C of our problem, is 80 degrees based on our chart, right, from here to here. Okay, consequently, this motor, because of this, would show us that it does not meet the standard. So we could either do one of two things, right? We could change how we want to offer it as to the class that it is. The rating would have to be reduced, or the cooling system improved before it could be put on the market and sold as a Class B motor. Okay. It also says, as this sort of a follow-up to this, it may be rewound using Class F insulation. And as a very last resort, size may just have to be increased overall, okay, to, because we're talking about an average, right? So, those are the options that a manufacturer would have. And this would be the things that would be carried out prior to production of a machine when you're trying to make the determinations of class and so forth, and how the particular machine is sold. He says, the final word of caution, temperature rise standards depend not only on the class of insulation, but also the type of apparatus. It could be a motor, a transformer, or a relay. The type of construction, whether it's drip proof, totally enclosed. We haven't really talked about that too much detail, but that's coming. All machines have a particular enclosure based on the environment that they're going to operate in. And so, that is a consideration. So the type of construction and also the field of application. You know, different machines have different classifications. You know, mil spec, military grade, commercial, industrial, and all of those vary. And you know, in my experience in past lives and working in this area, you know, I know that, for instance, mil spec products had a, you know, much stricter requirements in terms of material and specifications that they were able to make, because, you know, if you're in a situation where, you know, operation of something is critical, you know, maybe the mil spec has to also, it has to work in a desert, and maybe it has to work in a frigid environment. So, you know, the specification standards are a part of it. And then the last thing here, let me just read this and see if I understand it myself. Consequently, the pertinent standards must always be consulted before conducting a heat run test on a specific machine. And he says, see figure 610. What is that all about? Oh, okay. All right. So this is an example of that, and you know, it's being showing a situation to simulate a particular environment, you know, this water spray environment. Okay, so that's 6.9. We have one more section, 6.10, and we'll wind this chapter up.